Hi friends, welcome back. So today we will see another video on PCA or principal component analysis. So basically this notebook is based on banknote authentication, right? So we will be doing a detailed analysis on this. So yeah, the abstract that is about data so were extracted from images that were taken for the evaluation of an authentication procedure for banknotes, right? So this is some information about the data set. So data were extracted from images, again all these things taken from genuine and forged banknote like specimens for digitization. An industrial camera usually used for print inspection was used. So the final image have 400 by 400 pixel due to the object length and distance to the investigated object. A grayscale picture with a resolution of about 660 dpi were gained. So Wavelet transform tool were used to extract features from images. So this is the source of data set that you can also use, or we will be using this link directly in our notebook. So if we check the link, so here you can see that this one, this is the banknote authentication, right? Subject area computer dataset multivariate associated task is classification, real is attribute type, total 5 attribute that we have, and there are some detail of the dataset, right? So let's go back. Yeah, we talk about attribute information, right? So variance of wavelet transformed images continuous, skewness of wavelet transformed image continuous, right? Good kurtosis that we have, kurtosis of wavelet transformed images again continuous, and entropy of images continuous class, and then class is integer. Now let us start by importing the relevant library. So first is matplotlib.inline, importing numpy as np, pandas as pd, matplotlib.pyplot as plt, seaborn as sns. Now reading the banknote dataset in a data frame. So columns equals to that where skewness, kurtosis, entropy, and class. Df pd.read csv, we are directly reading this link inside our notebook, right? And data banknote authentication dot text. Okay, so index call that we are providing false and name equals to columns. So if I get this link and to check this out, just copy it here, right? So you can see that the text data that we have is this. So we are directly importing this data into our notebook, right? And name equals to again columns. Now let us use seaborn displot to analyze the distribution of our columns. So fax plt dot subplots 1 4, figure size is 10 by 13, 10 by 3. Now visualization for one, this one, right? So sns displot for variable, so this is for variable visualization, right? Bins equals to 10, xs equals to 0. Visualization 2 is for skewness, similarly for kurtosis, similarly for entropy. So here you can see that how the data that we have looks like. Now that we have a univariate distribution done, we go ahead and determine the pairwise relationship in the data set. We use the sns.pairplot, analyze the distribution. Also we add u to the distribution with the class call. Now sns.pairplot df and u equals to class. So here you can see that the colorful pair plots that we got here like this. So you can see that for each variable, like for variable that we have, for skewness that we have, for kurtosis that we have, right? And blue one denoting 0 class, and yellow are denoting 1 class. Entropy you can see here, and the finally class here. Now we separate the target variable class and save it in the y variable. Also the x contains the independent variable. So x equals to df.ilog, right? So here we are getting all rows but column from 0 to 3, right, on their values, and for y all rows and fourth column, right? Now splitting the data in test and train set. So again to get that we are importing train test split from model.sklearn. Now x train x test, y train y test, train test split, right? xy test size, test size we are passing 0.2, that is 20% is our test size. That means 80% will be definitely our train size, right? And random state, again we are passing an integer, that is 10. Now we use for our this one, that is scaling the data using the standard scale. So from sklearn dot pre-processing we are importing a standard scaler. So xtrain sd standard scaler dot fit transform for xtrain. Similarly xtest sd for standard scaler dot fit transform for xtest. Now generating the covariance matrix and the eigen values for the PCA analysis. COV matrix equals to np dot cov xtrain st.t. so the relevant covariance matrix, right? Printing covariance matrix in new line, right? Now this is covariance matrix, okay? And similarly generating the eigen values and the eigen vectors. So evals ev vectors, right? np dot line algorithm dot eigen cov matrix that we are applying here, print eigen vectors, right? And printing the eigen values. So if we talk about covariance matrix, right, this one, okay, so here you can see that the covariance matrix that we got and the eigen vectors, that this one evac. So here these are the eigen vector that we have and the eigen values for them. Now the cumulative variance explained analysis. So total equals to sum evals variable expression equals to I by total, right, multiplied by 100 for I in sorted evals and reverse equals to true. Now cumulative variance explained, that is cum vari xv variable is containing the np dot cum sum, right? And in which we are passing variable expression and printing cumulative variance explained. So this is cumulative variance expression, right? So finally the next is plotting the variance explained by the principal component and the cumulative variance explained. So here you can see plt dot figure fixed size 10 by 5, plt dot bar range 1, eval size plus 1, variable explained, and alpha is we are defining 0.5, align is center, label we are passing individual explained variance. And then you can see plt step. So these are step ranges 1, evals dot size plus 1, right? Cumulative variance explained, that we have applying in mid, label we are passing the same as explained cumulative explained variance. So y label are containing our explained variance ratio, whereas x label containing a principal component. So here you can see that the legend, that is log equals to best, and plt tight dot tight layout. So this way you can see that this is nothing but our cumulative explained variance and these are nothing but individual explained variance, right? So this way we can get that. Now eigen pairs equals to np dot absolute we are doing for evals of I, evax from 0 to I, right? And 0 row tan I, and for I in range length of e values for, so it will be looping with all the values. Now eigen pairs dot sort reverse equals to true, right? So this we got based on this slicing, okay? And this is basically from 0 to n minus 1, that is 4. Now we have is generating dimensionally reduced data set. So w equals to np dot stack, right? Eigen pairs 0 1 dot reshape 4 1, okay? Eigen pairs 1 1 dot reshape 4 1, printing matrix w, right? And the value of w, then xsd pca equals to xtrain sd dot dot this w, and xtest sd pca equals to xtest sd dot dot w. So here you can see this the matrix that we got, right? Now xtrain sd dot shape, y dot shape, x sd pca dot shape, xtest sd pca dot shape. So here this is the shape for our all xtrain sd, y shape, and xtest pca and xtest sd pca. Now we will use support vector classifier, logistic regression, and naive bias, right? So first thing, importing our SBC from SVM. Now storing into the clf.fit for xtrain sd and ytrain. Now printing before PCA score, so clf score xtest sd and ytest, clf.fit xsd PCA ytrain, and printing after PCA score, so clf.score xtest SDPCA and Y test. So before PCA score we have the accuracy, and after PCA we have the accuracy. So this is near to 100%, but after PCA we got 81% of accuracy. Now from sklearn.linear model, importing this logistic regression, containing it into a variable model.fit, that means logistic regression.fit xtrain sd ytrain we are passing here. Now before PCA again we are calculating the model score for xtest sd ytest, and similarly for after PCA model score xtest sd PCA ytest. So here you can see before PCA we got 98% of accuracy, but in case of logistic regression after applying the PCA we got 77% of the accuracy. Similarly, if we check for naive Bayes, right, that Gaussian naive Bayes, so model we are taking this Gaussian naive Bayes, same thing we are doing model.fit xtrain sd ytrain, and printing before PCA score model.score xtest sd and ytest, model.fit xsd SDPCA ytrain, and this will go for after applying PCA score. So again before PCA score it was 84%, and after PCA score we got 74% of accuracy. Now in the given data set we trained model with the original and dimensionality reduced data set, right? The effects of PCA can be clearly appreciated on fairly large data set. Okay, the learner are encouraged to try the above the various large data set out for themselves, right? So you can also test it out, which will definitely help you, right? And we done the main concept of PCA in the banknote authentication. So this was all about this video. Hope you got slight idea about how can we apply the PCA, right? Stay tuned, we'll be back with the another video. Thanks a lot.